Hi everyone. So today is actually going to be a lecture. This is lecture 4. And this is going to be, I think, the last kind of, I don't know. I want to say kind of trivial lecture, but it's not trivial, just preparation lecture. Starting from next time, you're going to kind of see a sequence of results. Each of them is kind of more surprising that we can prove. But today is still kind of we're building up for that. And we are going to move from local study, like study points, to study the function fields themselves, like to prepare ourselves for the global gameplay. So last time, just as a reminder, we talked about valuations, evaluation rings, maximal ideals and places, and residue fields. So, that's not going to work. So evaluation, strike 2. Evaluation, right, is this function that takes a function, like an element in the field, but we think of this as functions, and produces an element from an ordered group. Finally, today we are going to restrict ourselves enough so that this will be Z, but not yet. And to evaluation, with evaluation, you have this evaluation ring, which consists of all functions for which the evaluation tells you that the evaluation of that element is non-negative, which we think of as this element is defined at that point. And so this ring is the set of all, or ring, the set of all functions that are defined some ambient point that we are abstracting. We saw that this is a evaluation ring, which means that it has a unique maximal ideal. So with unique maximal ideal, which is the same thing, but with inequality. Right, and we show that we can move from one to the other, like each of them is, I'm kind of starting with evaluation and derive everything, but we can go from everywhere to everywhere. And maybe the most, it's the newest and also maybe slightly more subtle notion is the notion of a place. And there is a place. So what's a place? So the type of a place is a function that tries to evaluate. So it takes a function, and it outputs, I mean, the way we define the places from the evaluations. If we just finished that last time, we did one case, but the other case is trivial. So a place takes a function and technically it should produce something in a field, which we called K, union infinity, only 0 goes to infinity. No, sorry, that's K union infinity. But the way that the place was constructed from the evaluation or the evaluation ring and the maximal ideal, what we did was to define the place, the field that we go to, which we call the residue field, like that. So this is the residue corresponding to our evaluation. Right. Okay, so that was last time, and it was defined, if you remember, just by extending the projection map. So we took O, an element in O to its coset, and an element that is F and not in O to infinity. Right. Good. So any questions about that? I mean, last time we were just finished proving that. There is one more slide in the notes from that unit. Now I'm at unit 7, but that give you continues our ongoing example, y squared minus x cubed plus x. And there I kind of compute the place that corresponds to the 0 point that I told you only one thing about it, which is v0 of x is 2, right, if you remember. Okay, so that was that, and now we are at a new unit. As I said, we're going to kind of go global now, and the unit is called unit 7. This appears in that unit also as a recap, the ramification and residual indices. Okay, so we are going to consider two indices. You'll see what I mean by indices, which are going to kind of go with us for the course. And they will have some geometric interpretation that we'll talk about, but you will see. So that's what we are going to do now. That's unit 7. Oh, by the way, I don't know if you noticed, I uploaded like a video about Artin's approximation theorem to YouTube, like a whole lecture that I don't want to do here because it's important, but it takes an hour. It took an hour and then some. And it's not that, like, it's interesting, it's nice, it's important, but it's not like hard. It's really easy to follow. Like, so I didn't want to spend time on that which will enforce me to kind of move quickly on things that are more complicated here. So I just put it there. I'm going to state the theorem later on when I need it, like next time. But if you want to see the proof, you can see it in the YouTube, but I'm not assuming you're seeing it, okay? Just, you will have several of those, I think, for the course, because it requires like 20 weeks or something, not 14 or 13. So that's my way around it. But, you should see it. It's really, it's kind of, if you want to understand how you play with valuation, it's like a very good kind of example, okay? 1 hour example. Also in the homework, the first question that you have there is the first step in the proof. If you get stuck in the homework, you can see that. But anyhow, so let's move to talk about the ramification and residual indices. And these talk about, and we are going from this point on, try to talk about field extensions, right? So far we have this one field and everything attached to it, valuation and so forth. We will care about field extensions. So let me start with a little discussion. So let's say that E is a subfield of F. And let's say that you start with some valuation of the bigger field F, to some ordered group, infinity as usual. And I don't know if you remember, but the notion of evaluation, I mean, for a function to be evaluation, you have two properties. You want triangle inequality and additivity. And these are things that are like intrinsic properties. So like for every A and B in F, something should happen. Like, whatever, but something should happen. The valuation of the sum is that, and the larger given the minimum, and valuation of the product is the sum of the valuations, but it's an intrinsic property. So definitely you can restrict V as a function to E, and it will still be a valuation, right? Because if it holds for every pair of elements in F, it will hold for every element in E. So let's note it like that. V restricted to E as a function. As a function, it goes from E to the ordered group, maybe to a subgroup of it or whatever, but maybe also here you go to a subgroup of gamma, I don't know. So just it's okay to write it like that. So this thing is also a valuation of E now, because it's just easier. And now you can ask, okay, I have a valuation of the lower field. What is its valuation ring, maximal ideal, and place? Like, how can I get them from the corresponding objects of E? Right, so what do you think? So OE, what should it be? Like, there's only one thing that it can be. Exactly. I mean, I'll show that in a second, but if you have this motivation in mind, then what's written here, are all functions in E. I'm restricting my set of functions only to E, not to F. All functions in E that are defined at the point given by O. And this is the same, all functions in E that are defined in the point given by O. So it's like tautology, if you understand what's going on. But it's also a tautology by definition, because the way you proved it is you just kind of open up the definition of this little thing. So O of E, right, is all elements just by definition, is all functions in E, such that, the valuation ring that comes from a valuation is defined like that. Right, this is what we have there, but now we are talking about valuation which is denoted by V sub E, like that. But this is exactly the same thing as V of A larger than 0, right? It's just a restriction of the function. And that's it, because this is the set of all elements in E that are also in O, because that is the condition for being in O. So starting from evaluation, if you restrict it as a function, something very simple happens for the evaluation ring. You just restrict it in like the set theoretic sense, and also ME, right? The same thing. What should this be? Okay, good. Yeah. Because I just put inequality here and you're the same. Now for places, something more interesting is that I want to talk about. Something less trivial. So let's go through that. So what is the induced place? Like coming from VE, what is the induced place? But note, I could have done it in different orders. I could have started with OE and try to figure out to kind of like get back VE and so forth. You can start with any direction. I just chose to start from here and derive all the other relations. But it's a fun game to play to see that everything is kind of consistent. I mean, it has to be, but anyhow, the induced place, that's so as a function, let's denote it like that. So as a function, I don't put this line on purpose. It's not like I'm going to restrict phi, because I didn't get a restriction of phi, I got a restriction of v as a function, right? You gave me v, I restricted as a function, and now I want to use the general rule given a valuation, namely v sub e, what is the place, right? So I should start from E, but where should I go to, like generally speaking? Exactly. Even union and but yes, exactly, because we have this special rule, the general rule that said if you start with evaluation, you can compute its O and M, which are denoted here by OE and ME, and then the place, I mean that's what's written here, actually for general case, and then the place that is induced by V and O and M is this thing. It's like the function from E to this residual field, which is defined by on OE you just take the coset, and on E minus OE you go to infinity. And that's the general rule of how to get a place from evaluation, and you kind of want to compare it to what you started with, right? So just as a reminder, phi, like the original phi, it came from F to O modulo M, quotient by M, like that, right? So these are different function types. Not only the domain is different, but also the range is different. And I want to understand what's the relation between this field, it's a field, right? Because it's a maximum ideal, it's the residual field, this field and that field. And what do you think will happen? Not as clean. Extension, right? So this is going to be a subfield of that. Okay, so we'll see that now. So what I'm claiming is that I'm going to say something about it in a second, but what I'm claiming in this particular case is that the residue field, the induced residue field, is always a subfield, so you write it like that, of the original residue field. I claim there is an embedding, like a bijection from here to here, a ring homomorphism, which is a bijection, a field homomorphism from here to here. And the map is kind of obvious. I'm claiming there is a bijection. What's the bijection? So you take an element here. So an element here looks like something A. A is in OE plus ME. Right, this is a general element here. And where should you map it? I mean, what can you do, right? Exactly. Because A is also in O, because OE is part of O, because it's an intersection with E. So it makes sense to write A here. But the only thing you can do is like to be less refined, like increase the cos. Because this is a subset of that, right? Because this is intersection of that with E. So this is the map. I'm claiming it's well defined because I use kind of representatives to define it. So I need to just show for one line that it's well defined. And then what I will do is to prove that it is indeed a bijection so an embedding, it's one-to-one, not bijection. So it's one-to-one, it's an embedding. But then I will tell you that it's a general thing that if you have a ring homomorphism between fields, it must be one-to-one. But once more. So let's first prove that this is well defined, and then let's prove that this is one-to-one, and then I will say it was one-to-one to begin with. It has nothing to do with this example, but I don't want to use that like initially. So why is it well defined? In order to show that it's well defined, I need to take two representatives and show that they go to the same place, right? That's what you want. So if well defined, if you take two representatives A and B, so let me write it like that, then what can you say about A minus B? Right, exactly. It's in ME, which is a subset of M, because M is the intersection of M with E. And that's it. So this means that A plus M is B plus M. Right, so the representative doesn't matter. Why is it an embedding? So the tailor-made argument for that is the following, but then there is a general argument. So take A plus ME, take any element that is mapped to 0, like that is mapped to M, which is the 0 of this ring quotient field, the way that we represent this field. Right, so this is an element in the kernel of this map, right? So let's look at it. I want to show that A is also in ME, namely only 0 goes to 0. Then, right, so A is in M, right, because it is mapped to A plus M, but if this is M, then A is in M. But also, A is in E, it's like in OE, which is a subset of E, because A comes from here. So it's a subset of E. And that's it, right? A is in M, A is in E. So this means that A is in the intersection, which is M sub E. So the only way that A plus ME goes to M is if A was in ME to begin. But do you see another way of just showing that with nothing to do to this example whatsoever? Like if you have two fields and you have a field homomorphism between them, namely as rings there, it's a ring homomorphism. One goes to one and it respects the addition and multiplication. I claim it's always the case, probably you know that, but you just forget. It's always the case that it has to be an embedding. Right? Exactly. So let me just say that because it will appear again and again. And that's kind of, in a sense, that's the better way of doing the embedding part here, but it's nice to play with the definitions. So this is just a remark, a field theory remark. So the remark is that if you have two fields, any fields, like I'll call him F and E or something, but whatever, any F and E. If you have a ring homomorphism between two fields, so these are fields, and this is a homomorphism between them, respects addition multiplication, and it ends 1 to 1. We have this always the underlying assumption. And then I claim when phi is 1 to 1, it's like a monomorphism, if you want. Not necessarily onto, but it's a mono. And you know that because you know that the kernel Y, so the kernel of any ring homomorphism is what? Is an ideal, right? Is an ideal of F, but F is a field now. So yeah. Who are the fields ideal? Right. So these are like 0 and F. These are the two ideals that field has. but 1 goes to 1. So I mean, it can't be it can't be all of f. Right? Not everything in f goes to 0 because 1 goes to 1. So that rules out because 1 goes to 1. So it can be that everything goes to 0. So this means that the kernel is 0, which is another way of saying it's a 1-to-1 map. Okay, so you don't really need that. That's kind of a non-professional way of doing this. So you just remember that if you have, I mean, you only need f to be a field. But if you have a homomorphism from a field to somewhere, then okay. Good. So with that, I'm ready to define the two indices that we have. Very important indices. It's not clear why they are interesting at the beginning, but you'll see. I'm actually kind of disappointed by the markers. Okay, the one that's here is better. So I'm going to give two definitions now. They're very important, and I'm going to leave out the most important fact about them to the recitation. Okay, I'll tell you why, but we are going to kind of take as with faith. So the first definition is about the residual index, and the second one will be about the ramification index. So we just proved that if you have a field extension f over e, then you start with evaluation of f, you can restrict it to evaluation of e, and then you can see what happens to the places. You have phi and phi of e. So this is phi, this is phi of e, and we just proved that this is a subfield of that. So the index that I'm referring to is the index of this as a subfield of that field. Okay, that's the index that I'm talking about. Let me write it down. But so let V be evaluation of a big field, and E a subfield of F, as we had before. The degree. So you look at the residue field of the larger field and the residue field of the smaller field, and the index here means these are two fields. I just as a reminder, these are two fields, and this is a subfield of that. So you can think of this field as a vector space over that field. Right? You can kind of ignore the multiplicative structure of this field and only multiply elements from here with kind of scalars. And you can also add them up if you don't ignore the additional. Right? So every field extension gives you a vector space just by ignoring the multiplicative structure of the bigger field. And that, just as a reminder, tells you what's the dimension of this vector space. That's it, over this field. So what I'm claiming, so this thing, I'm not claiming anything, this thing is called the residual index of V, and you kind of need to say over E, really, because V doesn't encode the information about E. So, right. Good. Questions about this definition? In a sense, this thing, just looking ahead, I mean, as I told you, like when you do algebraic geometry, what happens is you kind of assume everything is algebraically closed and you don't worry about that. And when things are algebraically closed, this is going to be equal to that. But in general, it's not going to be the case. We are constructing codes over F49 or something. And so the residual index, in a sense, will tell you, how much the field of constant, like the answers grew potentially when you take an extension, when you look at more functions. You'll see. But so that's kind of something that's very much related to the fact that we're working with finite fields or fields that are not algebraically closed. So you don't see it usually in algebraic geometry. You do see it in number field, algebraic number field. If you took some course about it, you may, I don't know. It may remind you of something. Anyhow, the other definition, there are two indices, and they are very different in nature. So that's the index in terms of vectors, field extensions, and this is about index in terms of groups. So this is the ramification index. Okay, so now just by extending the valuations, forget about the places. I mean, we could have defined this before. So let V again be a valuation and D a subfield of F. As before. So note, so it's a note within a definition so that it will make sense, like a pedagogical note. Note that what can you say about this or with respect to that? Right, so this, just to make sure that we understand, this is the image of this map. I mean, it doesn't necessarily have to go to the entire group. Right? It could be subgroup of that. And then it's almost the answer. And then when you restrict yourself to E, right, only 0 goes to infinity. So you restrict yourself to E, the image is also going to be a subgroup of that, but it's also going to be what? Subgroup of that, right? Because if you take any, I mean, you want to show closeness, say inverse and close to product. So if you have two elements here, you can just go back to E. They gave you these valuations. You can take their product in E. It stays in E and look at the valuation. You got the product of the valuations. So it is a subgroup of that. And so what index should I define? Like a subgroup. So this is a subgroup of that. So the index of the larger group on its subgroup is called the ramification index of V, again over E, because V doesn't include information about E. Okay. And it's absolutely impossible to see it from the dry definition, but this has something to do with tangents. So like geometrically. So this happens also in algebraic geometry. And this is kind of usually one, but when it's not one, it means that the curve and the function that you could think of is not like talked about here at all. At that particular point, again, is kind of completely abstracted by the group, are meet tangentially like many times. So if this is 2, then it has multiplicity to a 0, a function that has something to do with what's written here, has multiplicity 2 with the curve, which has something to do with what's written here. It's not apparent from what is written on the board. But I'm just saying that these two things actually capture something very interesting. And we'll see that, but I just need to define it first. So this captures the fact that we work over finite fields. So this talks about the field arithmetic in a sense, and this talks about the geometry more about the geometry. Yes.
What you mean that there are two curves, and you mean that there's a function, there's a curve, and there's a tangent that said many times. How does E and F capture a set function or a curve?
Yeah, I know, not yet. Yeah, right. I mean, it's not only that I can't say it yet. I need to kind of be more specific about that. So I need to consider this notion of a function field that will happen next hour, and this is kind of a building up to that. Once you have when you will see this notion of a function field, I will tell you how it's related to a curve informally, and functions on the curve. Usually you think of two curves, right? Not a curve and a function. So you look at the 0 set of the function, it gives you another curve, and there you get the two curves. And no. No, we will see. When I get to that, I can tell you. I think in our case, E is going to be like the rational function field, and f is going to be the actual curve, like one of the point, and then the function, well, we'll see. It's not there yet. I mean, it's still like, it's like a Lego, and it's still like all threaded around. I need to kind of put it together, and only then we can see. So this definition by itself has something to do with what I said about multiplicity, but it's not, doesn't capture it yet. But we're on our way. But you would agree, right, that this index is very much different in terms of types than that index. Right? This is essentially field extension stuff or vector space stuff, and this is groups. And also there is another obvious index, right? The index of E in F, which is kind of, well, you know, it's kind of the global thing, right? V is, in my mind, is a point. And F and E are not, they're like, F has more valuations than just that V, right? So F and E in my head, and you will see what I mean later, are global stuff. V is the local stuff, and F over E captures something global. And what I want to do is to relate the index of F over E, the ramification index, and the residual index. We are going to do it like in a very strong sense later on, but I just want to give the first basic theorem, which I'm not going to prove because it takes like 40 minutes or something, half an hour, and it's actually a very good material for recitation. So we'll see it in the recitation, yes. Right, because V encodes information about F. So
Why do you think about this? Or you don't just
I mean, saying V is more specific than saying F. Like you can say the ramification index of V as an element of F over E or something like that. But you don't need F there. And you do need V, and okay. But it's a property of V really, and E. But usually E is kind of fixed and V moves around, so it's kind of this is usually not even been said. But let me give you the theorem, like without the proof. It's called proposition. We should raise it to a theorem at some point. Proposition 3, and so say you have as before. So let V be a valuation of F. And E, a subfield of E, of F. Then, so what I'm claiming is that the product, that doesn't make sense. Yeah. Yeah, that's okay actually. The product of the residual indexes with the ramification index is at most the index of F over E. This is a very strange theorem. 3 different types of stuff going on here. This is something that has nothing to do with V and E, something global. For every V, this should hold every valuation of F, really, and a subfield of E. And this is like a field extension in terms of like functions. There are functions here, and you take the field extension. And what I'm claiming is that this is upper bounded by a product of something about groups and something about, again, field extensions, but of constants, like F5 and F49. No functions here in a sense, right? This is where we get the results of the evaluations. It's a very weird theorem. But there's only like one way to prove it. If you are forced to prove it, like someone tell you have to prove it and that's it, then there's only one thing you can do. What can you do when you look at this? Sorry? Right, so you want to somehow, I mean, this is a vector space, right? So you want to somehow cook up from here basis elements or vectors, and from here vectors, and combine them in such a way that they are independent and they are less, and the number of them is less than that. And that will tell you that. But it's not so clear how to get this, because I mean, these are functions, these are like F5, and this is a group, like Z. So it's a very good exercise for the recitation, because then you have to go back over all the definitions and kind of take the group index and cook up functions here that relates to that and so forth. It's really insightful to see. And because of that, I'm leaving it to Tomer, and he'll do it. Maybe today or next time. Okay, but that's, we take this with faith. You trust me. And with that, we can actually do one more step towards the finally setting up the stage to our what's called the function field. So let me continue here. Later on, by the way, we're going to, again, when we instantiate ourselves to a function field, we're going to prove equality, but this is inequality. But in a sense, you can find several places or valuations, same thing, whose sum of those things are equal to that. But we'll see. We'll talk about it later on. I mean, okay.
How do you think of each of those?
Yeah, I can't yet. Yeah, no, I really want to, but that's why there is, well, yeah, I just, yeah, it's not, it's premature. I can't. I'll just tell you one thing. What you have in what someone has after in 2 weeks or something, you'll have the following picture in mind. You have a curve like that maybe, and this is the XY plane. And you can think of this, so this is a line, but you can think of so what are the functions on the line? And you don't have Y, only X. So the functions that you care about are rational functions usually. So you can take on this line rational function. This is the functions that we'll work with. If you only have like one variable, you know, what can you do? That's what you can do. So that will be E, kind of related to your question also a little bit. And F will be essentially like in the example that we did, you have this equation here, and you can look at its coordinate green and take its fraction field, like we did. Yes.
So F is like the regular, would be the regular function on this curve, right?
No, they will have poles. Yeah. O, given a point, O will be the regular functions on the point.
Okay,
Because there are no regular functions. Locally regular. These are all functions you can show because it's only algebraic that.
This thing is like local, this language?
Yeah, with the Zariski topology maybe. But I'm not, I don't want to think, I actually think of this as all functions in X and Y, subject to the relation, you know, between Y and X given on the curve, like we had last time, right? We had like all functions in X, and that's what I said, all functions X and Y for which, you know, Y squared is equals, you identify it with X cubed minus X. And then what's the point is? The point is if you take, so for me, evaluation on F is a point here, right? It kind of tries to capture the point. And then when you restrict it to E, in a sense, what you do is you take the projection down. A sense. You kind of substitute for Y this value and get a function in X, really. And so this is V sub E. Again, everything completely informal, okay? But just, and what I kind of just said is I kind of connected properties of this point on the curve with this point on the line, which is the only curve that you have in one variable. And there is another point that kind of seems to be related to that, which is this one. And if you take the sum of these, of both of these points, you'll get equality. Like if you take the projection of one point down and look at all points lying above the point that you projected to, and you sum over the product of ramification and residual, then you get that. Yeah.
And what do you mean when the index here is not zero? That means that the curve is flat, locally flat, X amount of times.
Which this is non-zero?
No,
that one, yeah. It just means that it's one, yeah, zero is not. I'm not sure.
The x-axis is tangent, but
it's
like
not.
A horizontal line is tangent. That's what you mean?
It's not tangent, maybe, right? It's not tangent. Like for example, here you have the tangent line. That's 2. right? And these two are 1. And that's a singular point that you don't want to look at it. But never mind. There's nothing to do with this now. But anyhow, just a nice kind of trying to connect geometry to algebra. It's too premature. But just that you'll have something in mind that maybe is not connected. You'll know that someone has something in mind at this point, and then we'll see how it's related. But it's really premature. It's kind of remarkable how quickly you go from all of these to something that's really interesting. But so I want to state a corollary, to prove a corollary. I mean, as I said, Tomer is going to do the hard work, and I'm going to cash on it. Oh, but maybe I need before the corollary. Yeah. Sorry. I mean, before that, I need to kind of prove a little claim, and then. So the claim is, I'm going back to ordered groups now. Forget about all of that. It's a claim that we could have stated and proved when we talked about ordered groups, but it was without context, and now it's with some context. So I rather do it here. So here is a nice fact about ordered groups. So let's say, I mean, I'm going to use it with these 2 points. So let's say that you have 2 ordered groups. One is a subgroup of the other, like in our case. These are ordered groups also, right? And assume that the index is finite. And we know that it's finite in our case, because, I mean, this will be a finite extension, and so this one is finite. In our case, f over e will be finite all the time. So assume that the index of the larger over the smaller group is finite. Then, kind of a curious little claim, by the way. Then if the smaller group is isomorphic to Z, which we call discrete, maybe, well, the valuations we've started to call discrete, then, I mean, if the smaller group is not too large, I think of this as a very kind of small group. I mean, it's infinite, but it has to be infinite. We proved if it's ordered. So if the smaller group is small, then also the larger group is small. Because, I mean, it has to be not too large because the index is finite, but it can't like go to something that's larger than Z, which is a bit weird. Okay, and moreover, like adding to that, if the smaller group is trivial, it's 0 group, nothing there, like 0 is there, then also the larger one, like the smaller one kind of, because of the ordered structure and the finite index, it really kind of restricts the larger group to being larger than the smaller group, much larger than the smaller group. I mean, it could be Z and 2Z or something, but not more than that. Right, it's a weird little theorem, right? Like, I don't know if you'd expect it, I don't know. Right, so I'm just saying that when you have a pair of ordered groups that are relatively equal size, like the index is finite, then in these particular 2 cases where the smaller group is 0, 0, then also the larger group is 0, 0. So let's prove this. It's easy given what we did, but let's just see the proof. So let's just give this a name. So let n be the index itself. It's a finite number, but I want to give it a name. And if you recall, we proved that the map phi of n, phi sub n, from gamma to gamma, I'm only looking at the bigger group now, which maps an element to adding it to itself n times. Remember what we proved about this? So we proved that this is an order preserving, well, it's order preserving, it's kind of obvious, but monomorphism, which is not so, well, it is morphism. It was a very simple fact, but adding an element to itself n times is a homomorphism, and it's actually a monomorphism, and it's order preserving. I mean, you'd expect it, right? I mean, the only way 2 things will go to the same place if there's kind of a cycle there, which will break the total order that you have on the groups. And so forth. But we proved that. So, okay. So now let's take, before proving each of these, I just want to say something, and then both of them will follow. 1 and 2 will follow. So take any element in the larger group, right? And if you consider it in the quotient group, namely look at gamma plus delta, then n times gamma plus delta. So that's an element in the quotient group now, right? I took an element in the big group, I took its coset, and I added it n times, which is the size of the quotient group, which is the order of the quotient group. And what happens when you take an element in the group to the power or multiply if it's additive to the group size? It goes to the neutral element, right? I mean, G, usually you see it in multiplicative. G to the n is 1. If n is the order of the group is, the order of an element divides the order of the group. In particular, an element to the power or times the group size, in the abelian case, you write it as times. The group size is just the neutral element, which is what in our case? Delta, right? Because that's the coset, the neutral coset. So you have this, and this you can write as n times gamma plus delta, right? Because this is how you define addition when you move to quotients. And but n times gamma is just another way of saying phi n of gamma. Right, so this is because what we said, n times gamma plus delta is just n times gamma plus delta. This is how you define the addition of, when you define the quotient of a group. And just to relate it to the definition of phi n, which it doesn't kind of appear here, this is exactly phi n of gamma. So this, from all of this we get that phi sub n of gamma for any gamma in gamma is in delta. Right, because we took any gamma and we just proved that phi n of gamma is an element, I mean, it goes to delta, so phi n of gamma is in delta. Namely, phi n takes the large group and maps it to the small group. Right? And that's funny because, this means that phi n of gamma, on one hand, it's a subgroup because of that. Well, it's a subset, but it's also a group. So it's a subgroup of the smaller group, right? Because phi n maps all of gamma within delta, maybe not onto delta, but within delta, and it's a group homomorphism, so its image is a group. So you get this group relation. But on the other hand, we proved that phi n is a group monomorphism. So this is actually isomorphic to the big group. See, it's like we flipped it. Like now gamma is a subgroup of the bigger group. Gamma is a subgroup of the smaller group. It's magical, right? I don't know, it's weird. It's one of these things that you kind of get each step, but you don't know what happened. And from here, this follows immediately because, so for example, point 2, well, if delta is 0, then gamma as a subgroup of it, or isomorphic to some subgroup of it is also 0. That's because it's a monomorphism. We proved last time that phi n, where n is the right, where n is the right, we proved that for every n, I think. This is an order preserving monomorphism, which is really heavily dependent on the fact that these are ordered groups with total order and so forth. Yeah, so that's kind of something that's non-typical, like. Okay, and secondly, actually it's like falsely maybe, and then we take the break. Well, it's also kind of the same. If you know that delta is isomorphic to z, so this is z, so gamma is a subgroup of z. Because of that, gamma is a subgroup of z. So it has to be isomorphic to z or 0. Right? So gamma is isomorphic to z, in which case we are done. Or something that we need to exclude, gamma is 0. But gamma can't be 0, right? Why can't it be 0? because then if gamma is 0, that was the bigger group before we flipped it. Then delta would be 0, the subgroup of the 0 group, and delta is isomorphic to Z. So there is this kind of cycle and tension between them. Yeah, and that's it. Right, so that's a weird claim. And after the pref, we are going to use it to do the last step before building to function fields. So yeah, let's meet after the break. Okay, so let's continue. Great questions, but I'm going to erase any residue of those. Right, and also actually someone remarked that this was a weird way of doing it. I mean, we just proved that gamma is a subgroup of delta, and we know that delta is a subgroup of gamma by assumption, and so they're just isomorphic, and we don't need all of these. That was a bit weird to do. Good, so thanks. So there is an easier proof. Okay. So with that, we are ready to. Right. Yeah, I don't know why. I mean, we only need these two cases from here on. So maybe that was what kind of directed someone to do it like that, but they're just isomorphic. That's it. Yeah. And in particular, right? That was a bit weird to write like that. So now we are ready for corollary 5. And maybe just to remind you, before taking the corollary and prove it, recall that evaluation is trivial if it sends everything to 0, except 0, which always goes to infinity. Right, this was the first example of evaluation, the trivial one. Everything goes to 0. It's not to say that it's not interesting. It will be interesting, but I just want to give it a name. Usually when something is trivial, you want to omit it from everything, but actually a good valuation. Like it will correspond to constant functions, right? A constant function is everywhere defined. Well, the non-zero constant is anywhere defined, everywhere defined, and it has no zeros, which is exactly saying that v for any point v, that function is 0. But anyhow, never mind that. So here is the corollary. Let f be a finite extension. Our extensions will be finite of the rational function field. So T is just a transcendental element or symbol, okay? And E is a rational function field in T, and F is a finite extension of it. In the sense that the index is finite. Then every non-trivial valuation V of F that is trivial on K is discrete. What's written here? You are looking at a finite extension of the rational function field. Okay. So what will happen is the following. The rational function field we are going to completely understand. We're going to understand all of its valuations in the recitation. And this will be our starting point. So now we're looking at finite extensions of that. Okay? So it's like a number field and stuff. This is like Q, and these are number fields over Q. For our case, this is the rational function field, the easy case, and we're looking at finite extensions of it. This will kind of correspond to curves in general. Anyhow, when what I'm saying is that if you take any valuation of f, well, there is the trivial one, but every valuation of f other than the trivial one, well, I don't know quite what to say about that, but if I know that it's trivial on K, then it is discrete. Now, the way I think about it is, K is F5, is a constant. So valuations on K should be trivial, because evaluation tells you if you have a pole or a zero, and constants don't have poles and zero unless it's a zero function. So the evaluations that I have, for me, K is F5 when I see this theorem. It doesn't matter, but K is F5. So obviously every evaluation of F is going to trivial on K. I mean, it's not interesting. That's the only evaluations I care about. So what I'm saying is that every non-trivial evaluation of F that has this relation with K is discrete, namely it's a number, it's in Z. Discrete means that its image is a subgroup of Z. And this is what I kind of promised you, that gamma at some point, and that's actually going to be soon, but after this is going to be Z from here on. Namely, it's a number. There is the valuations goes to Z. And that number has something to do with the multiplicity of that point in a sense. Okay, but yeah. So let's prove that. Again, these are all kind of preliminary results to what's coming right afterwards. So let's do the proof. And I'm going to use something from the recitation. As I said, we need to kind of understand the evaluations of KT if we want to use that. And we will understand, you will understand it today. So by proposition 3, the big one, the one that should be a theorem, we know that the product of this with something else, if I take this index and I'll multiply it, but I don't want to, with the index of the residual fields, that is smaller than F over E. Right, we prove that something stronger, even if you take the product with the residual field indices here, index here. And this is finite per assumption. I'm taking F, which is a finite extension of it. This is by assumption. Okay. Now, by claim 4, the one that's, this is its proof with the weird little claim about ordered groups, we know that since the valuation of, so the image of the valuation over the large field is non-zero, right? We know that V is non-trivial on F. Right? Saying that it's non-trivial means that it has something other than zero. We have that also the lower image, the valuation on the lower field is non-zero. I put it here. Right? We did the contrapositive, but you know, if the larger is zero, if the larger is zero, but the smaller is zero, so if the smaller is non-zero, anyhow, they are isomorphic. So since they are isomorphic, if this is not zero and this is not zero, that's a better way of saying that. And now I'm in my comfort zone. I mean, it's not yet your comfort zone because you haven't been in the recitation. But in the recitation, you're going to completely characterize all the non-trivial valuation. This is non-trivial valuation over the rational function fields. Right? So V is a non-trivial valuation of K, of E, but this is just the rational function field. And you will prove that if you're actually going to find all of them and you'll see them, but what will happen when you'll see them is you'll prove that they are all discrete, which are all discrete. So at least for the rational function field, all valuations are discrete, and there is the trivial one, namely V of E is isomorphic to Z, but then that implies immediately, because they are isomorphic, that also the bigger one, the valuation applied to the bigger field is isomorphic to Z. It's either this or the improvement that are actually isomorphic. And that's what we wanted. We wanted to prove that every valuation of F, which is non-trivial, and is trivial on K, is discrete. I mean, what you'll see, I mean, you can ask, where did you use the assumption that it's trivial on K? So it's trivial on F5. So what you will prove in the recitations is you completely understand all the valuation of this, which are trivial on K. That's what I meant. All the valuation of KT, F5 of T, which are trivial on K, all of them, well, there's the trivial one and the other ones are discrete. And that's where I use it. I used it, actually Tomer will use it, not me. Questions? Hey, Tomer. I just told everyone what you're going to prove today. Is it today, by the way? Like the product of indices smaller than f over e next week. But this one is today about the rational function field. Yeah. So today you'll see the rational function field here. And then next week, it's this one. You see, it's not really a recitation, right? It's like one more lecture, really. But okay. So any questions about all of that? These are kind of different moving parts that I'm going to combine together now. Yes. Yeah, good, good. That's what I said. So already this is the fact that it's trivial on K, right? So that's actually Tomer is going to use. So in the recitations, you'll understand all the valuations of this, which are trivial on K.